Take a look at this function here, and we're going to try to do a good job graphing this. So the first thing here, let's find out the roots of the function, and that's when the function is equal to 0. In that case, only the numerator is 0, and so that only occurs when x equals -1. That's pretty easy. The domain of the function, what values can we plug in? Well, the only problems would be if we'd be dividing by 0. But if you check in here, setting the denominator equal to 0, it never happens with the quadratic formula, because when you try to solve this denominator equal to 0 with the quadratic formula, you get a square root of a negative. So you get no solutions to the denominator equaling 0, meaning you can plug in anything. So the domain is all real numbers. Y-intercept, that is when we plug 0 into the function, and we would end up with 1 over 1, which is 1. Okay, next, critical points would be when the first derivative is equal to 0 or undefined. Now the first derivative you're going to get from just doing a quotient rule, and it's pretty straightforward on this one. So critical point, when is this equal to 0 or undefined? So first of all, equal to 0 is when the numerator is 0, and let's factor a negative x out of the numerator. And so when that's equal to 0, it would either be when the negative x is 0, which would be x equals 0, or it would be when the second term, x plus 2 equals 0, which means, of course, x equals -2. We could also get critical points when the derivative's undefined, but again, this denominator is never 0, so that doesn't happen in this case. Now, for graphing purposes, we're going to want to do a good job of graphing, so we not only want the x-coordinates, we want the y-coordinates of our critical points. So we plug the 0 back into the original function. Well, that was the y-intercept. We know it's at 0, 1. And the other point, plug the -2 in, and if you put that into the original function, you get -1/3. Okay. So we like to know, are these local mins, local maxes? When's our function increasing, decreasing? That's the first derivative test. So we're going to set up our number line here with those critical values of, let's go with -2 and 0. And we're going to check out what's the first derivative. Okay. Again, we know that those two values had 0 for a first derivative. Let's plug in then a value less than -2, so f prime, say, of -3. And if you do that, we only care about the sign of this thing. So if you evaluate this, what you find out is it is in fact a negative number. Plug in, say, a -1, and if you do that, you find out actually this comes out to be 1, but a positive number is the important thing. And plug in, say, +1. Oops, these are all to f prime. So f prime of 1, the slope is in fact a negative value in this part. So what we know is our function is going down, going up, and then going down again. So what that tells us is right here, that has to be a local minimum value here at our -2. So the -2 critical point we found, it has to be a local minimum. Similar idea, increasing then decreasing here around the 0, so this must be a local maximum value. So those are going to be important points when we graph. This also allows us to answer this increasing decreasing question. We know our function is going to be increasing from -2 to 0, and this is interval notation, and it will be decreasing before the -2, so -infinity up to -2, and it's decreasing again from 0 on up, so 0 to +infinity. So that's how we write that part. The other thing we want to check is using a second derivative test. So we're going to put in again these critical values of 0 and -2, but this time into the second derivative. Now how did I get this? This was a quotient rule and major simplification. It's pretty ugly. So if you plug a 0 into this, actually it's pretty easy to see that the second derivative of 0 gives you a -2 out of it, and so that means it's concave down at that critical point, meaning you must have a local max, which agrees completely with what we had up there using our first derivative test. Similarly, if we plug in the critical value of -2, that's a little messier, but if you plug in a -2, we get a positive value this time, indicating our function is concave up, and we already knew that its first derivative was 0, meaning horizontal tangent, so that must be a local minimum value, again agreeing with our first derivative test. Okay. Inflection points, possible inflection points, a little cautious here. We're interested, when is the second derivative equal to 0 or undefined? And as I told my classes, these are sometimes called stationary points, which are the possible inflection points. Okay, so first of all, it's never undefined, so it's just looking at when is that numerator of 2x cubed plus 6x squared minus 2, when is that equal to 0? Now it's a cubic. It's not a fun one to try to do. The only option really here is Newton's method. Okay. Now if you try Newton's method, what you're going to end up with here are values of -2.879 and -0.653. And the third one would be 0.532. So notice we get 3 points, which makes sense for a cubic function. Now we do want to graph this, so we're going to want to know what are the corresponding y values. So I'm just going to make room for the y values. So you have to plug each of these 3 values into the original function, and when you do that you get a -0.293. For this one you get a positive 0.449, and for this last one you get a positive 0.844. Okay. Now to find out, are these actually inflection points? When is it concave up? When is it concave down? Again, we set up this number line with these 3 values here, the -2.879, the -0.653, and the 0.532. Kind of yucky. So we knew the second derivative was 0 in all 3 cases, and now it's a matter of evaluating the second derivative around this here. So say, for example, we plug in a -3, and what we end up with when you plug it into the second derivative, it's a number less than 0. Okay, and what does that tell us? That tells us that we have a concave down function at that point. Similarly, plug in a value in here such as a -1, and you find out it's positive. Over here, oops, sorry, these were second derivative we're plugging these into. Here, plugging second derivative, or 0 into the second derivative. Actually, we did that already. We found out we got a -2. And this last region, say let's plug in 1, and you find out that that one's positive. So, going back through here, we said that was concave down, then we have concave up, concave down, and concave up again. So we can write our intervals. When is this concave up? It's concave up then from this -2.879 up to -0.653. And I'm going to save a little time here. So I've written down the other regions of concavity. You can stop the video if you need to check. This also tells us that the points that we knew were possible inflection points, concavity changed at every single one. So in fact, all 3 of those points were inflection points since concavity changed. The last things to check before graphing, vertical asymptotes. Of course, this is when we'd be dividing by 0, and for this particular problem, that never happened, so we had none. Horizontal asymptotes, we're going to take the limit as x goes to infinity of the original function, and if you do that, you might want to use a little L'Hopital's rule, for example, and you end up with, say, 1 over 2x plus 1, and you see it's going to 0, both for the positive infinity and negative infinity. So that tells you there we had a horizontal asymptote at y equals 0. And now we can ask this question about global minimum, global maximums. We know that this function, from up here with our first derivative test, went down, up, and down again. And because we know our function has these asymptotes at y equals 0, we know that it's going to go no lower than this local minimum and no higher than the local maximum, okay? Which we found the y values of before, okay? So our global maximum we found occurred when f was in fact 0, which was 1. And our global maximum was when we plugged in the -2, and in that particular case we got -1/3. So that's as big and as small as the whole function gets. And now that tells us the range of the function. If the function is bounded here from -1/3 to +1, our range is -1/3 up to +1. Notice the interval notation brackets I'm using. I'm using these brackets rather than parentheses to indicate, yes, we actually get down to -1/3 and up to +1. Okay, so now let's try to put all of this stuff into a single graph. Okay, because we found our range here only going from -1/3 to 1, it probably makes sense to scale this, I don't know, maybe by 0.2 might make sense here. 0.2, 0.4, 0.6, 0.8, and then we get up to 1 here at the top. Okay, and then likewise going down a -0.2, -0.4, -0.6. Actually, I don't even need to go that far. And on the y direction, I think going by ones will be fine. 1, 2, 3, 4. Similarly, the other direction. Okay. So now let's put on the important points that we know are going to be part of the graph here. So we had our root at x equals -1. Okay. We have our y-intercept at +1, which, remember, also happens to be our local and global maximum. So let's put that in there. All right. And let's see what else we got here. We know we've got the local minimum was at -2, -1/3. So -2, -1/3 is about there. -2, -1/3. Okay. So that was both a local and a global max. And then we have our inflection points which were a little bit messier here. So let's try to copy these guys down here. We had our first inflection point at a -2.88 roughly, and at a +0.29. It's almost right here. Okay. Let's see what's a good way to, let's write it here. So we have an inflection point, as I said, -2.879 and -0.293. So that's that point. Oops, that's a pretty bad job. That point doesn't belong there at all. It's negative. Let's try it where it belongs. Down here. That's a little bit better. Something seemed odd. There we go. Just move this in here. And then we're going to put our other inflection points in a similar manner. Only do it correct the first time. So there's our other inflection points. And then we need to put in, we know that we have a horizontal asymptote right along the y-axis. And then I think we're ready to put the rest of this in here. We've got, of course, our concave down in here. Yeah, that's pretty bad. Then it's concave up to the minimum. This is hard to draw on this thing. And then it's concave down again to the asymptote. Ugh, that's sloppy. And then here, concave up to the asymptote. So other than this bit of slop, there we go. That's a little better. Pretty good graph there. Fix that pin. Okay, so hopefully yours looks similar.